A comet known as, with the designation 3I or 2025 N1 with the name of Atlas, was discovered on CCD images obtained on 2025 July 1st with the Asteroid Terrestrial Impact Last Alert System, or ATLAS telescope, the Schmidt telescope with a half a meter mirror located in Rio Hurtado, Chile. It was around magnitude 18 at the time. Pre-discovery images were found back a full month on pre-discovery Atlas images, with the earliest being on June 5th of last year, taken at Sutherland, South Africa. The designation 3I indicates that it was the third interstellar object discovered to pass through the inner solar system after the stellar appearing object 1I Oumuamua and Comet 3I Borisov from 2019. So A/2017 U1 is 1I Oumuamua. That was a preliminary designation. It was discovered a month past its perihelion. The closest approach to the sun was 0.255 astronomical units at magnitude around 19, and it faded rapidly. Its faint brightness precluded a lot of observations, and it was last seen with the Hubble Space Telescope in early January 2018, recorded at magnitude 25 and a half at Mauna Kea on 2017, November 23rd. Comet C/2019 Q4, or 2I Borisov, was discovered in late August 2019, a couple years later, at magnitude 18, 3 months before perihelion, where it was closest to the sun at 2 astronomical units. And it was heavily observed while peaking near magnitude 15 around perihelion, combined with pre-discovery observations of 2I Borisov from Palomar in December 2018. That comet was followed for over 23 months, last seen at magnitude 25 with the Hubble telescope on 2020 September 30th. We cannot know what star or stellar system that Comet 3I Atlas came from because of the complex motion of distant stars in our Milky Way galaxy, but we know that it came from the direction of Sagittarius in the Milky Way's outer central bulge. From calculations by Sam Dean, an amateur astronomer, with Comet 3I Atlas moving at 58 kilometers per second, its trajectory in the last million years would correspond to about 197 light years. And looking for a host star would mean looking at stars within about 300 light years, stars that could be dozens of degrees away in the sky now from the origin point due to stellar motions within the galaxy. So we just don't have radial velocities for the vast majority of stars in our current catalogs, such as Gaia. So, for example, the closest Gaia star to the position from where the comet came lies about an arc minute away, and it's currently about 4,200 light years away from us with a radial velocity that suggests it could be 29 degrees away from that point when Comet Atlas would have been at that distance some 16 million years ago. So we're not going to find out where exactly this comet came from. So in general, this is the third interstellar object that we have found. So all comets and everything else that we observe in the inner solar system, even the outer solar system, is bound to the sun, right? And so, so these objects are interesting, and we're going to discuss, why we didn't know any interstellar objects until 2017, and now we have three. So how many are there? A lot of questions there. So Comet 3I Atlas reached a total visual magnitude of 9 in the latter part of 2025, the last couple months, and continues to fade now as it recedes from the sun and the earth, being around magnitude 14 now in early February of 2026. It should fade to about magnitude 18 in May of this year, when it'll be lost in the sun's glare for a few months, and then around magnitude 20 when it reappears in the morning sky in September 2026. So we still have a few months that it can be observed, and astronomers will continue to do that. But once it's fainter than 20, it's going to be mostly just measuring the position and the brightness from that point. Okay, so let's introduce who we have here. We have 8 people with us for a discussion of Comet 3I Atlas. In addition to our 4 YouTube channel members present today, Casper and Carl are from Tucson, Arizona. Mike Myers in Germany. I'm in Massachusetts right now. And I'll introduce our 4 panelists that have joined us. So Quanji Ye is a research scientist at the University of Maryland and Boston University with a general interest in the smaller solar system bodies, including asteroids, comets, and meteors. He has observed all three interstellar objects using a range of telescopes. Emmanuel, is it Yahin?
Oui, Johan.
Zahin? Okay. My French is not so good. I'm sorry. Is a professor at the Star Institute at the University of Liège in Belgium and director of research at the Belgian National Science Foundation. He's a group leader of Cometa for comets, meteors, and asteroids. They study small bodies in his research group. He's also director of the TRAPPIST robotic telescopes that are used 50% of the time devoted to monitoring of small bodies and 50% for planet transit search. And those telescopes are in Chile and Morocco, right? Martin Cordiner is a research associate professor in astrochemistry and planetary science at Catholic University in America and at NASA Goddard Space Flight Center in Maryland. His research aims to understand the chemical composition and physical properties of solar system bodies, interstellar clouds, and circumstellar environments. Kecheng Zhang is an astronomer at Lowell Observatory who studies comets. In fact, all 8 of us study comets. So that's one thing that unites all of us. And where it's hard to say that any one of us is an expert on Comet 3I Atlas. We all know about it. We've observed it. We are studying it. But we've decided to bring this group together to just have an open discussion and so that the public who's watching this video might learn something, and the 8 of us may learn something as well from each other. So let's get started, and we'll just hop in. We have some talking points that we all put together. Why don't we just start with 3I Atlas being an interstellar comet? How unusual is it in terms of the composition with respect to typical comets? Any guys want to step in?
Anybody
Manuel?
Nickels?
Yes. So, of course, something which is very interesting with an interstellar comet, it's coming from another planetary system. So you would first guess that it could be completely different because it's coming from somewhere else. We don't know exactly where and around which kind of star. But in fact, Borisov and 3I Atlas, when they were looked first, you can see the usual things you see in solar system comets, but you might see them in different abundances, relative abundances, and you might still see some differences. So there are things that make clearly that this object is a comet, and by the behavior, the aspect, and in the composition, you recognize things, but there are also very interesting differences that are probably coming indeed from the system from where it's coming from, with peculiar fingerprints, let's say. So we are not completely lost when we look at it because we see things that we are used to see, but maybe in different relative abundances and maybe with also a different behavior when getting close to the sun.
So you mentioned that there was an elevation of nickel and iron, correct?
Okay, so yeah, so this is something we have been doing with colleagues also, like Cyril Opitom from Edinburgh University. So in our team, we are more specialists of the optical spectra of comet. We do that since 20 years with the very large telescopes. So I've seen a lot of spectra of bright comets, about 25 in the last 20 years. They really look all the same, basically, when you look at them. But it was really shocking when seeing for the first time the blue part of the spectrum of 3I Atlas, because at 3.5 AU from the sun, so still pretty far when water is not outgassing and so on, the spectrum in the blue was totally dominated by bright emission lights of nickel and iron. And we discovered nickel and iron in our team, in fact, in 2021, in all the spectra of comet we had obtained with the VLT, but it was missed because it was not looked at. And in fact, in Liège, we are trying to make an atlas of lines in the optical spectra. And we noticed that some lines were non-identified, and trying to identify it, we found these nickel and iron. But in solar system comet, it's very tiny amount. While in the spectrum of 3i Atlas, those lines were super bright, brighter than everything else. So about 100 more times brighter than in solar system comet. And so that has been quite surprising and of course extremely exciting also.
Martin, what did you find from your
Yeah,
observations?
so when I think of of comets, I think of these kind of dirty, icy kind of snowballs drifting through the solar system, and how can we understand their composition? Ideally, we would like to fly out, take a piece, bring it back to the lab, and it's tantalizingly close to be able to do that with a comet or an interstellar object. It's in the grand scheme of things in the universe, these come past very close. They're just like almost close enough to reach out and touch. But unfortunately, you need very expensive and very carefully planned missions to send a spacecraft out to do that sort of thing. So what we're left with is our ground-based or space-based telescopes, which have very powerful, in many cases, spectrometers or spectrographs, so that we can break up the spectrum into different wavelengths. And then we can study those different wavelengths and pick out what different chemicals are present in this object. And unfortunately, there's no one telescope that can cover all of the wavelengths. Ideally, we would like to just point one telescope, get the whole picture. So we have to do a lot of detective work with the telescopes that we have. We have to point them very accurately at the comet. And these telescopes have huge apertures in many cases, and we're able to pick up the signals from these very faint objects. But the data that I was initially focused on was observations in the infrared region of the spectrum between about 1 micron and about 5 microns. And in this region of the spectrum, you see vibrational emission bands from different molecules, different gases in the coma, which emit these vibrational energy photons. Now, the James Webb Telescope is the most powerful infrared telescope that we have. It's above the atmosphere. It's not affected by terrestrial atmospheric contamination. It gives us sensitivity to some key molecules, which are actually really quite difficult to observe in ground-based telescopes. It allows us access to water and CO2 and CO. Those are the three lines that come up the strongest in the JWST, the James Webb Telescope data. And so those were the first species that we looked for with Webb in 3i Atlas. And we got a really beautiful spectrum. I was blown away by just how nice the JWST data were. We were able to detect just incredibly strong CO2 outgassing, relatively weak water outgassing. Now, this was just immediately like a really clear sign that there was something quite strange about this comet or this interstellar object at the time. At the time, we don't really know what it's made of at all, but this JWST data showed us tons of CO2 and just comparatively very little water outgassing. It was something like a ratio of 7 to 1 in terms of the CO2 to water. Now, it's very rare in our solar system to observe comets with CO2 to water ratio greater than 1. So here we see 7, and immediately we just knew that we were looking at something that's a little bit different. It's containing the same basic compounds as our comets do. And as we build up more information at more different wavelengths, we see other compounds like the CN radical that we typically see in comets. I think C2 has been detected, NH, and of course OH, HCN, methanol, these kind of molecules. But the ratios that we see them in are actually quite distinct and a little bit different from the ratios that we've typically been seeing in the past in our own solar system comets. So from that perspective, it's really interesting to think about why that is. Is it to do with the original environment that 3i Atlas came from? Was it very rich in CO2? Was there some chemistry that produced more CO2 than other molecules? Or are we looking at some kind of evolution of the body as it passed through the interstellar medium? It changed and became more CO2 rich. Maybe there are some ideas that you can do cosmic ray processing of the surface to do that sort of thing. But another quite compelling explanation is that maybe what we're seeing as we look at 3i Atlas we're seeing the gases in the coma, and maybe the CO2 is being released more readily than the water. So we see this very rich CO2 rich coma, and we don't see so much in the way of the H2O, because H2O, water, is less volatile. It doesn't get released into the gas phase as easily as CO2. You need a higher temperature. So from my perspective, it's still a strong possibility that there's something about the surface of 3I Atlas which prevents the water from being able to readily sublimate or be activated. So that's how you can end up with a very CO2 rich coma. We're still piecing the details together, as I said.
So this is a more gassy comet, not very dusty. Is that correct?
Oh, it has plenty of dust. I mean, the first observations of 3I Atlas were of the dust coma, right? When I think, the early discovery images showed some evidence for little coma. It was the HST beautiful optical images that by Dave Jewett, and he showed that the dust coma was very expansive, and it had this kind of unusual sunward, what they call the anti-tail feature, which you don't see in that many comets, this kind of plume of dust in the sunward direction. So it's a dusty comet for sure. It's gassy, and it surprised me in terms of how much gas and dust it has inside of it.
But you have sublimation of ices that push the dust off the surface when the comet's far from the sun. So,
Yeah, that's right. Yeah.
So the CO2 presence, it tends to sublimate at a further distance out than water does. So did
Yeah.
we get more water as it got closer to the sun, as it got closer to perihelion?
Yeah, it did. I mean, I'm not involved directly in a lot of the observations that were discovering water. We got this one time period with JWST back in August when we saw very little water, loads of CO2. And then after that, it was kind of picked up by optical and UV wavelengths, and also radio telescopes. And even one of the Mars assets, MAVEN, was detecting, I think, the OH very strongly. So maybe optical or UV observers have some more info about how the water production changed over time.
Yeah. So Emmanuel,
Yes, what was a bit surprising is that it looks to us that the comet took a while to really kick in the outgassing of the gas and keeping kind of a compact inner coma, pretty bright, and then suddenly 2 weeks before we lost it in the glare of the sun, and was still about a month before perihelion. This last week at the Very Large Telescope, we saw a really huge increase, and we saw all the usual species coming out very quickly. So it comes back to this idea that there might be a kind of a crust on the comet that was not allowing the ices below to be really well released. Maybe it was colder also, but we should not forget that this object is in our solar system already since a long time, but of course getting closer. And something that observers have noticed is, and we still have to put all the pieces together, and it's difficult to understand, but some have noticed that it looks like the composition after perihelion, so after passing the closest point to the sun, changed. Like suddenly we could see much more C2 than before. In fact, it has been characterized before perihelion as a C2 depleted comet. And then after, with our telescope, the TRAPPIST, the 4th of December, first time I could point it, I could see a lot of usual gases like C2, C3, so not depleted at all, in fact, and quite normal. So it looks like it took a bit of time for the stuff to get released, and probably this usual stuff is coming with the water. So what is very different with this comet is this CO2 and CO very rich layer, maybe. And then it took a bit of time to get the usual stuff out. A bit unfortunately, we did not see the comet while it was really close to the closest point to the sun, 1.4 AU. By the way, we have been very lucky with this comet because this is the first interstellar comet getting so close to the sun and the Earth. And of course, for us, when we want to study the composition of the comet, closer it is to the sun, more ices are sublimating, and more you can see minor species that you would not see if it's not outgassing a lot. And it was good for Atlas, especially because after perihelion, we could pick the comet up about 2 weeks closer to the sun, let's say, than pre-perihelion. It's why people have the thought that after perihelion, the comet got much more brighter. In fact, what we are going to publish is that it's very symmetrical. In fact, the outgassing before and after perihelion, it's really symmetrical. It's quite amazing how well shaped it is, but it's getting extremely, the activity a month before perihelion is picking up really fast. And in fact, at perihelion, it was a pretty big active comet, like 310 to the 29 for the water. So a very nice comet, in fact, but that we could not see because it was behind the sun. So we still have to analyze all the pieces. Also, something which is different with comets, difficult with comets, and we don't see it very often claimed. It's always you have to know where was the comet, at which distance from the sun, because different species start to sublimate at different distances from the sun. And this one is different. And so we can expect in the different time where things are starting to show up. So in the literature we see a lot of information, this comet is not that or is this, but all the time it's very important to know at which point it was with the distance to the sun. Because as Martin was saying before, it was very rich in CO2, 3 AU, but the 3 AU water is not sublimating a lot. And also CO2 is extremely difficult to observe from the ground, as it was explained. Now the best instrument to do it is clearly the James Webb, but how many comets have been observed with the James Webb yet? Not many, less than 5. And now we will be able to build up a statistic about CO2. I think CO2 has been clearly a missing piece since the last 50 years, because CO2 is impossible to observe from the ground. So with James Webb, it's really a new tool, and we might be surprised about this CO2, because the CO2 information very often was coming from second thought, indirect measurement, and so on. It's always better to measure directly, and with the James Webb, this is a fantastic instrument to do it. And yeah.
And I assume that we will be able to detect CO even further from the sun. That will be also interesting to see how its composition varies as it's.
You mean post-perihelion?
Yeah, post-perihelion gets further and further from the sun.
Yeah, for sure. I mean, CO2 is a bit less volatile than CO, so we expect the CO2 to probably shut down somewhere in the range of sort of 6 to 10 AU. That will still be a relatively easy detection, I think, with JWST. The CO lines, the CO band at 4.7 microns is a bit weaker. But as you say, we do expect the CO to keep on outgassing while the water and the CO2 shut down. So even out beyond 10, maybe up to 20 AU, it'll still be possible to detect that CO. Yeah. So it gives us an interesting prospect that we can keep on monitoring this comet, and I hope people do carry on. You know, it's still well worth observing how it changes over time like this.
Yeah, it's certainly unique to have any interstellar object. But this is brighter than the other two that we've seen. So we've been able to learn more about 3I Atlas than the other two. So
yes, and something also incredible with this comet, it has been attracting so much interest because it's coming from another planetary system that there is really a huge amount of data, of observation of any kind. And we realize, in fact, that we nearly don't have as many and as good data for normal solar system comets. So we see that we should also study probably better our comet of the solar system, like far away also from the sun and coming closer. And this is really something important to better understand and compare the comets between themselves. Also, it's why this comet will also tell us more information about our own solar system comet by comparison.
Um, Carl, you had a few interesting questions about composition versus interstellar objects.
Yeah, I mean, one question I had was if we were studying 3I Atlas but had no idea it was interstellar, would we have suspected on it based on its composition that it was of an interstellar origin? Because we do have comets that are bound to our own sun that possibly, I mean, people have postulated that maybe they were interstellar originally. But based on what you saw with the composition, would your little red flags have gone up saying, hey, this thing might not have originated around the sun, just based solely on composition?
I think it's a great question. I like this
Mhm.
question, and it takes me back to this unusual comet called R2 PANSTARRS C2016,
Mhm.
I think it was. And at that time, it was sort of it was a bit of a joke, I think, maybe an in-joke in the comet community to say, well, it's so weird. It's like an alien comet. We've never seen anything like this. It has such high quantities of CO, CO2, and N2, so these hypervolatiles. So it was raised at that point in a couple of serious publications, like this is such a weird comet that could it be an interstellar comet? No interstellar comets have been observed at that time. So we didn't have really a good basis on which to hang that idea. Although there have been predictions for decades that interstellar comets should be out there based on how planets form and migrate in their disks and throw out these comets into space. Interstellar comets were predicted, but never observed. So nobody really took that idea seriously. So I think if you see a weird comet, you just have to put it in the category of weird comets because there's a lot of weird comets. Comets are weird in many different ways. Each comet is kind of distinct, actually. In fact, some are more weird than others in their ratios of molecules and how they outgas and how they behave and how things change as they evolve. So yeah, each comet is a bit different. So from my perspective, although there's a lot of weird things about 3I Atlas, um, I feel like it still fits into the paradigm of what we know about comets in general.
About the composition, a definitive way to make the difference would be to compare the isotopic ratio of carbon and nitrogen, for instance, of that comet with respect to solar system comet. Since 25 years in our team, we are looking for carbon and nitrogen isotopic ratios in very bright comet. You need very bright comet. And you see something very clear. All the comets of the solar system, Jupiter family or cloud comet, they have the same carbon ratio, carbon 12 to 13, is the same as what you find in the solar system in many different kind of objects, the sun, meteorites. The nitrogen in all the comet is enriched by a factor of 2 of nitrogen 15 with respect to the atmosphere of the Earth, and even more with respect to Jupiter. And this is a clear signature of these are solar system comets that have had some special chemical processes. So being able to measure the isotopic ratio in an interstellar comet like 3I could tell us indeed if this is similar or different. And we could expect some differences based on what you can find in the galaxy. We are working on a paper with our colleague Cyril Opitom. It's very hard to do, extremely difficult because we had to sum up a lot of hours on the comet. And it's not published yet, it's not definitive, but we might see slight differences that we could interpret as the fact that it is not indeed, that it is different from the solar system comet. So the isotopic ratio is really a tracer of the origin of the object, where it's coming from. In this CSI for the cops to identify a body if you have a skeleton, you can, by looking the isotopes, to know in which part of the Earth it was living, in part of the US, for instance, because it's really give you information about the origin. So isotopic ratio is a very good tracer of the origin of your object. At least the chemical and physical processes it underwent. So that would be a definitive way to make a difference, I think.
Yeah, I'm glad that Martin brought the case of C2016 R2 PANSTARRS, because that object I mean, we have back in the day when I was doing my dissertation, we have a detection of C13 through the 12 CO 2 to 1 rotational line, um, you know, submillimeter wavelengths, and we did get actually an isotopic ratio 12 to 13 that is very different from solar system objects. At that time, I didn't think, about, oh, it's interstellar. It's interstellar because the detection of C13 is what I would call marginal. It is above 3 sigma, but yeah, as you say, that specific isotopic ratio, 12 to 13, is, I think, a great way to chemically, not orbitally, identify whether something might be of interstellar origin or not, since that ratio is quite consistent.
2016 R2 was an Oort cloud comet. Is that right?
It's a long period comet. He came already, but of course it's a long period comet from the Oort cloud, but it's a returning comet. 16R2 came back. What was very special with 16R2, it was low dust and a lot of this CO ice, and the possibility could have been a chunk of differentiated objects with a lot of ice of CO and so on, like Pluto, but the orbit does not match with a collision, which could have been a nice explanation for such a weird object. Because we have always to think how these objects are there, and the interstellar comet, it's very interesting because it has been ejected from its system by which kind of process. And what is also extremely interesting is that the first interstellar object was not looking at all like what we would have expected. We would have expected a comet as the first interstellar object because there are many more comets than asteroids and so on. And we found something which was not active, very elongated, more elongated than any asteroid known, but that had also these non-gravitational forces and so on. And so what it was, it's still not clear today. There was a small body, but was it a piece of a broken planet? Was it an asteroid? Was it a comet? It's not totally clear. So these objects are super interesting because they are coming from another system. They might have followed the same processes, but they've been ejected also. And now what we can really see, it's emerging a new field of research because these three objects, they look a bit different. Borisov was kind of a normal comet, let's say. This one has strange specificities, a lot of CO2, a lot of nickel, and so on. And Oumuamua was even weirder. So what we can hope is that in the future, with these big surveys like LSST, the Vera Rubin telescope, we are going to detect more of these objects and start to do some statistics. So it will give a lot of clues about the other planetary system. And I mean, the prediction is that there are, of course, billions and billions of these objects wandering in the galaxy. And at the time we are talking, 1,000 probably in the solar system, but too small or too far to be detected. But yeah, the problem is when we want to do the compositional analysis, we need bright objects. And it was very frustrating for Oumuamua, super fast, no activity, no coma. He was better with Borisov, but really faint even with the larger telescope in the world, hard to get some information. We got some, and now we have 3i Atlas, which is for us really nice. There will be tons of papers again coming out with a lot of information about the composition. And yeah, so this is, by the way, interesting a lot also the exoplanet community, because these exoplanets have been maybe formed by the building blocks, comets, asteroids, like in our solar system. So we can have a link with this extremely exciting field also, because we have the chance with these exoplanets, comets, interstellar objects, but comets form in other planetary system that they are visiting us super close. So we can really get some more information of the planetary disk. And in fact, with the advance of the instrumentation, we see a lot of progress is being done also in the disks, in the analysis of the disk around forming planetary system. And we are going in the next 10 years to be able to really see those comets forming in those systems. It's already the case. Huh? There are more than 30 Oort clouds and disk discovered with comets forming. And Martin knows that better than me with ALMA. They've made fantastic things. They are going to be able to look for gradient of isotopes in it also and really learn how these systems are forming and the comets forming in there. So the exoplanet community is extremely interesting, but by what we are doing with these objects. It's good for us because it could be really good support from the TAC, to get time on the telescope to do them also.
Wait. Oh, sorry, Dan.
Go ahead.
Yeah, if I may chime in, because I think Emmanuel just mentioned a very interesting point there, and one very tricky thing about studying this object is that like it will be dominated by the brighter objects. And 3I Atlas is great, but sometimes we need to keep in mind that there are fainter objects that may represent a different population that can lose the attention because they're hard to find and they're hard to study. But we need to keep in mind that it's a huge mix of exciting stuff. Some are bright, big, and easier to study, and some are faint, harder to find, harder to study. And what we are seeing is can be a little deceiving if you are not thinking carefully, because it's always the brighter things that got find first and got studied first. So it's really kind of interesting exemplars that we find 3 interstellar objects, and the first one's faint and only was observed only for about a month or so, and now we have this nice bright comet that can even be seen with. I think there are even visual observations of it, if I remember correctly. But yeah, oh yes,
I've seen it visually.
Yeah,
yeah. When it was near 9th magnitude, I saw it in binoculars. Yeah.
Yep.
Oh wow. Yeah.
Possible around Washington D.C. area, I think.
Yeah. So I'll just throw in something here. So just for the general public who might be tuning into this, we've discovered thousands of comets that have been observed in the solar system, but they've all been bound to the sun gravitationally, right? Until Oumuamua was found in 2017. So that's what it makes this unusual. And I have a little side note here. I'll just throw in here. When I was a grad student, I took a graduate course at Harvard under Alex Dalgarno back in the early 1980s. And the course was on interstellar astronomy. And we all had to write a paper for the end of the course. And my paper I chose to write on was comets in interstellar space. And I speculated that so what happens in the solar system, we have a fair number of comets that go close to the larger planets, such as Jupiter, and they get ejected forever from the solar system, right? So they don't come back. But they're bound originally to the sun, and then they go very close. We use the same thing, the process with artificial satellites when we're trying to get to outer parts of the solar system. We have gravitational boosts, right? You go near a planet, it gives extra momentum and speed and to send them at higher velocities out. And that's what happens with comets that go close to Jupiter. So I speculated in my paper for this course that there must be a lot of other comets in the Milky Way, right? Going around other stars that get ejected and are just going through the solar system. And the thing is that it was a course paper. I never published it. And I thought, well, what's the point? I thought at the time, well, it must be kind of obvious, but I guess people hadn't thought about it all that much. And but I worked very closely with Brian Marsden for many years, computing the orbits of comets, every comet, as a matter of fact, for decades. And Brian and I always pondered, why aren't we seeing any interstellar comets? You know, we have all these comets out there, but and I want to bring Mike Meyer into the discussion here because you have some good questions, Mike, about you know, why and uh, why these three and what possibilities are there for the past and for the future.
Yeah, I mean, it's quite astonishing to have three interstellar objects in such a short time. I know it could be a statistical glitch, maybe, yeah, but we don't have in the space of time, it's just a few years, maybe a decade. Yeah. But when I'm looking back at the surveys and I think the CCD surveys maybe in the mid 90s or so, they already had a very good coverage, and we had some deep going surveys maybe back starting with the Palomar surveys were the first ones, and never such an object has been observed. And we now have seen that we have very faint ones. Maybe Atlas is a very bright one. I don't know. Maybe it's really someone on the brighter end. But as you said, one would expect you have the whole variety of objects, very large ones, bright ones, and very small ones. So it's quite astonishing. And as I'm dealing a lot with historical comets and searching for it and trying to find more of it, um, when I'm looking at for instance, in cometography, when we look back at those comets, of course, those comets for which we have an orbit, they are safe. They are not interstellar comets. But of course, there are a lot of objects for which we can't calculate an orbit. And for all of them, we assume that they are solar system comets. But could it be that maybe some of those objects have been an interstellar object? We don't know. We won't be able to say in any case. What is more interesting for me is that we already dealt with unconfirmed comet discoveries, and there are some interesting objects indeed, which are very strange and which have been observed by different people, and for which no orbit could be calculated. There's a very interesting object in 1879, which was observed by two people from the US, which saw an object which was more or less asteroidal, but showing a faint halo, yeah, moving across the sky, uh, maybe like a slow satellite or something like this. No orbit could ever has been calculated. The observations were too crude, and you couldn't calculate an orbit. So what was it? So either there are definitely objects which could have been missed. The thing I would like to ask the guys here from the surveys, maybe Kwanzi could say something about this, is we have a lot of archival data. Yeah, the MPC had a lot of observations stored of objects which we called one-night stands before, which is now those objects which could not link to others, and these are millions of observations. I wonder how many objects are buried there because they could not be linked. And the question is, in earlier times, nobody was really trying to link for an orbit that is interstellar. Yeah, we were always looking for, yeah, elliptical or parabolic orbits for comets. So shouldn't those orbits or the surveys now also look for linkages which are based on interstellar things? Maybe the MPC was rejecting such linkages before. That's an interesting one. Maybe we were looking just for our solar system objects and missed the other ones just because we didn't look at it. Yeah. A lot of questions, and I guess if we approach the observation or the search for new objects a little bit differently, also taking into account that there could be interstellar comets, maybe we find more even sooner. Of course, with the larger telescopes now starting to work, maybe also fainter ones.
Yeah, that's an excellent question, Mike. I have been wondering about the same question too, and as you said, there are a lot of so-called how to call it, single trackless whatever.
Yes.
In case folks listening, tuning into here, thinking, oh, there are really a lot of dragons going around. Those are the stuff that you only see on one night, but you don't see the other night. Maybe you just haven't got a chance to follow them up, or maybe you just don't think they're interesting. You just move on with your work, with your observation. You just send it off to the NPC or the Minor Planet Center, which is the international nerve center for archive for keeping all this data. And of course, it's all public. It's all public. It's not nobody's keeping them off, put in some corner. Um, um, and and Mike, as you said, I think it's only in the recent years that people starting first we know that interstellar comet objects are there. They are not like maybe one over 1,000 year kind of thing. They are happening, and we found three over how many? 9 years? Yeah, well, 9 years. Well, that's fast. And I do know like some of my colleagues that I know have been like running programs trying to link this single detections from different nights together, and I think they have some success. I was assume that if there are some obvious interstellar objects hiding in there, we will probably already know about it. But I guess maybe the challenge is there is really a lot of data to go through. Yeah, now we have much better computers, we have AIs, but still, you have some data, and some of those single detections could be false objects. It's not because somebody like something false object, but like when you have images, they could be artifacts and all sort of stuff. Things do happen. So I think it's a challenge to go through, this large, data set that we accumulate over decades, I guess, and try to mine something useful there, and then try to verify it. I guess that's maybe sometime somebody will write a paper to rigorously, discuss they're really interstellar objects hiding there. But since we are hearing them, I will assume that, okay, if they are hiding there, they must be hiding really well. But we know comets always hide really well. hide their true nature really well.
My point, my point of view, I think we will know soon, let's say in 5 years, because I think we might have reached a turning point in terms of detection of the object, better survey, because still, if you look the number of asteroids detected near Earth and so on, it's really exponential. So we still improve. There are many more facilities, faster computers. Of course, now really looking for also interstellar objects, because I'm not sure if the story is true, but I think Oumuamua was first rejected by the software, and it's someone that noticed that there was interesting and picked it up and check it and validated it. So with LSST coming online, so this very large 8-meter telescope that will screen the sky, do a photo of the sky every 3 nights, we'll see everything moving. So if there are more of these interstellar comets, let's say often, it will detect them most probably, and then we will start to build a statistic. We really, when the first one was detected, I thought, wow, that's incredible. The object is very weird. It will never happen again. Then we got Borisov, look like a comet. Fantastic. I thought, okay, now we will have to wait 10 years to have the next one. And no, it came just 3 years, 4 years after. So we are really, maybe we really reach a turning point, and we will know it, I think, very soon. In 5 years, if the discoveries continues to arrive, it means that we reach a level of detection better, and so on. Also, maybe in the past, I'm not so sure, but maybe in the past they were avoiding the Milky Way. And because there are so many stars, it's very difficult to identify an object moving through the stars. We notice it when we try to do the light curve of Atlas when he was just in front of the Milky Way. And by the way, as they are coming from other stars, all the stars in our galaxy, most of them are in the disk. So it's logical that Borisov was in front of the Milky Way, 3I Atlas was in front of the Milky Way when it was discovered. It was very hard to catch. So maybe in the past, indeed, many have been missed because faint and in front of the Milky Way and so on. So I think we just have to wait a bit, and we will see in the years coming. It will be super exciting, and I think probably there will be, of course, more faint objects that maybe for us doing composition will not be so interesting, but for statistic of orbits and so on, colors of object size, it might matter. But for the and type of object, asteroids or comets or something else. So that will be extremely exciting, and it's now that it is happening with the Vera Rubin telescope, and hopefully there will be good alert for everyone to go on the very interesting object, because this is crucial. Like Oumuamua, it was crucial to go fast because they are faint, going very fast, and then you can lose them extremely quickly. So we will have to be really clever and good with our way to catch up those objects and try to analyze them as fast as possible. So I think 3I is really the best we can hope for. Okay, it could even go closer to the sun and closer to the Earth, be bigger, but yeah, like McNaught Comet, of course, then it would be just fantastic. And yeah.
Yeah, Emmanuel, you're talking about Mike's background, which is the bright, very nice bright comet that
I saw from
that
I saw from Paranal. I stayed 3 weeks in Paranal. I went down and then went back. Went down for 1 day, went back in Paranal. It was an amazing comet, and nearly looking like that naked eye. It was just fantastic.
The funny thing is, I always wanted to see a daylight comet like McNaught really was, and I was spoiled by the weather from Germany, and missed all the more or less clear daylight comets. But I would never have dreamed to see an interstellar comet with my own eyes. So this was quite interesting, and we talked about the light curve before, and I was really a little bit disappointed shortly before it went into the sun's glare, as the light curve seemed to flatten out, and it didn't look as if it would make it into my reach for visual observations. And so I was very happy and to have seen it by naked eye. So my bucket list, the interstellar comet, is struck out. So now daylight comet still missing.
Now you need to hope for the next daylight comet being interstellar.
Definitely, yeah.
I'm probably going to buy lottery.
Well,
there is one that in 2017.
Yeah, there is one every 25 years statistically, but it could happen next year, in 2 years. But yes, so I had the chance to see it naked eye for 2 days, McNaught, in the shadow of the UT1 of the VLT, in the blue sky, very high in the sky, close to zenith. It was super hard to pick up because the eye does not know where to focus on the blue sky. So you are really lost. But then when you help yourself with the binocular, you remove the binoculars, you see where it is, then I could spot it. It was not, of course, very impressive. At night, it was much more nicer.
I saw McNaught's comet in January from naked eye from Cambridge, Massachusetts. Was able to first find Venus in binoculars and then the comet, and it was near sunset. And I was able to barely make it out naked eye, which was impressive. When the sun was still above the horizon, so that was amazing. But yeah, so these the question is about these old comets. We have records of comets going back millennia in the records, but we don't have orbits for these objects. You know, the question is, well, could one or two or more of them have been interstellar comets? Why not, right? And it's only in the last couple of 100 years where we really have orbits good enough to be able to determine. Even you go back to the 1800s when you get before photographs, before photography, most of the long period comets are just parabolic orbits, right? We don't know enough. The observations aren't plentiful enough, or they're not good enough, going back into the 18th century, 17th century even, to know. So, but moving forward, we have the LSST coming online. In the astronomical community, there's a lot of talk about the LSST, which is a survey telescope down in Chile, which is going to It's starting up now, apparently, and it's supposedly going to go very fainter than all the other survey telescopes. And they are claiming they're going to find a ton of interstellar objects. The people that make predictions, which of course still has to be seen. But it will be interesting to see what they end up coming up with. So that's in the next few years they're going to be going, and apparently this year they're going to really start flooding the Minor Planet Center with moving objects. So it'll be interesting to see. I wanted to also bring up the business. Emmanuel actually mentioned it. We were putting together some talking points. The Comet Interceptor. The Comet Interceptor European Space Agency mission is scheduled for launch in late 2028 or early 2029. This is from its website. It says, destination, pristine comet from the outer reaches of the sun's realm or interstellar object. It says, after launch, the spacecraft will be parked in space before moving to intercept a suitable, pristine comet. When the comet is near, the main spacecraft will release 2 probes to observe the comet from multiple directions at the same time. I've got a feeling an interstellar comet would be going too fast for for the interceptor. I think we'd be looking more at a McNaught type long period comet, or something maybe from the Oort cloud, but bound to the sun.
Yeah, so the idea of this space mission is to go with a spacecraft and fly by dynamically new comets. So it means a comet that never came in the inner solar system, so not a returning, a long period comet, an object that could be one of the most pristine we would have ever seen. There's been several comets flyby by spacecraft, but they were all Jupiter family ecliptic comets, or Halley, which is a Halley type comet. So it's a much longer period, 76 years, but never went close to a dynamically new comet. But there is the possibility also maybe to go to an interstellar object, and that would be, of course, extremely interesting. The issue is that the encounter needs to be done around 1 AU, up to 1.3, something like that, and on the right side of the Earth, basically, because the probe will be parked on L2 and wait the good moment to go to a target that we would have picked up. Maybe the target will be picked up so the launch is planned in 29, and all the important thing will be to select the best target. So to be sure it's a dynamically new based on the orbit, so it takes a bit of time to build the orbit and really be sure it's an object coming for the first time, or of course an interstellar object, then it's more clear about the orbit, but there are the problem of indeed having enough delta V on the spacecraft to reach such an object. But that would be fantastic, and that stays one of the big options, of course. There's been new computation, of course, based on 3I Atlas. Would Comet Interceptor been able to reach it? And unfortunately not, because it was still a distance too far. But the good news is that the spacecraft got a bit of an upgrade to get a bit more kick to maybe go a bit farther, a bit faster. And so that stays still one of the options, and that would be a first, of course. And that would be really fantastic because, of course, we study the coma, we study the gas and the dust coming from the nucleus, but to be able to see from close, and especially the spacecraft has a mass spectrometer on board that will sniff the coma and will measure the isotopic ratios, for instance, and these kind of things. So that will be fantastic. But the journey will be several months or years to reach the comet, several months, but the flyby will just be 1 day. So all the data most of the important data will be collected in 1 day. It goes super fast. And 2 spacecraft will be released before to get kind of 3D observation of the tails, the various kind of tails. There are, of course, many different kind of instrumentation on the 3 spacecraft. So 1 mother spacecraft and 2 smaller, 1 built by JAXA, the Japanese space agency. So the instrument is being built now. It's well advanced already. and I'm part of the COCA team. COCA, it's the Comet camera, which will be a high-resolution imager to take high-resolution images of the surface of the comet. Because all the question is such an object that never came close to the sun before, what kind of surface it has. Of course, the object coming from the Earth cloud toward us is heating up, of course, and when it reaches 1 AU, it has already been heating up, but we can still hope that we could see a much more pristine surface than Jupiter family comet like 67P that has been for centuries orbiting close to the sun, or Halley that was 76 years, but that is Halley comet is observed since 2000 years. So yeah, so we are really excited by that mission. There is a lot of teams working on this in Europe. Yes.
So we're gonna wrap this up because some of us have places to go. I just want to close here with the general public. There's sort of an elephant in the room. We're all a little bit hesitant to talk about this particular subject, but the question is, how do we know that 3I Atlas is a comet? Well, I think we've kind of, in our discussion in the last hour, we've kind of covered that. It makes sense that if you have a comet that forms around another stellar system, that you're going to have some different compositions. We even see a lot of different compositions within solar system comets. So it's not all that unusual, but there are certainly some unique things about Comet 3I Atlas. But there have been some discussions out in the public that has drawn a lot of attention to this comet, particularly by one person here at Harvard, Avi Loeb, has thrown out that maybe he started with Oumuamua because it wasn't a comet, it was elongated. Maybe it was an alien spaceship flying through the solar system. And he's kind of continued that theme through the two comets that we found, both 2I Borisov and 3I Atlas. Cometary astronomers generally are not on board with this. I can say almost universally we don't ascribe to this business, but it's been, unfortunately, the press has given a lot of attention to Avi Loeb talking about a possible spacecraft. This is not a spacecraft we're looking at. It's a comet. Is it a normal comet? Maybe it's a normal interstellar comet. We'll hopefully see more of these, but any of you want to chime in with any thoughts on this topic?
Well, the field of interstellar comet studies is still in its infancy, right? So every time
Right.
we get one, we just have that just insatiable excitement. What is it? What is this object? It's come from somewhere we have no idea. And this is why astronomy, astrophysics is such a fascinating field, because we have the ability to see and find new objects that nobody has ever seen before. You know, we're only human. We speculate. What is it? Could it be like something amazing? Could it be, aliens, this kind of thing?
Yeah.
You see unusual signals with radio telescopes. What is it? Is it aliens? Is it a pulsar? You have this debate in your head. It doesn't normally play out in the literature or in the press in the way that it has with 3I Atlas. 3I Atlas just got so much interest especially from certain camps putting out like news after news article. It could be aliens. It could be aliens, and the regular news media picked those stories up and ran with them. And why not? It's incredibly exciting. It brings interest to our field. But as a scientist, you're sitting there, you're seeing the information come in. We wait until we've got the information. The information comes in piece by piece. Oh, it looks like a comet. Oh, it has dust like a comet. Oh, it has gas like a comet. Oh, it has ice like a comet. Every piece of information we get is telling us it's a comet. And so the more information that build up, okay, it's a comet that's a little different. We expect it to be different, as you say. Interstellar comets come from different star systems, possibly the other side of the galaxy, possibly from 10 billion years ago. We expect this object to behave in different ways to our regular comets. So yeah, it's been an amazing ride, and the more information we find, the more comet-like it seems, but it also seems like an unusual comet. So yeah, it's been a lot of fun.
Yeah, I'd like to add that just for the general public, that if it looks like a duck, it's a duck, usually, right? And what we know about 3I Atlas is that it looks like a comet, it behaves like a comet, it has cometary species and composition that we have seen in solar system comets. And of course, it has its particularities from a compositional point of view, but one also has to remember that even though we have comet families in our own solar system, there are no two comets that are identical. There are variation of there are variations in composition in even in comets in our own solar system. And I think that humans since millennia have had this tendency that when something is new, strange, unusual, like I don't know, like thousands of years ago, in Scandinavia, they saw a lightning. They didn't know what it was, right? So they called it Odin, right? So now we're kind of in a similar situation where people are very prone to believe that it's aliens. We don't know what this is, it's aliens, And there's also wishful thinking in a way that people want to believe, that that this is a spaceship. Like I don't know, I don't really understand that reasoning, but that reasoning is there in the heads of many people. They just want to believe that, and it's hard. And when someone believes and thinks that way, it's very hard to argue with them, even though we have this big amount of data pointing to the direction that this is just a comet, just from a different solar system.
Caspar, I may add, for me, one of the strongest arguments, all the others you said are well, because it's the field of the others. But for me, we have three comets, and if they would have been spacecraft, they would have turned off their acceleration, apparently, totally before being detected, because they all follow the laws of gravity, maybe with very small amounts, which are usual for comets. So yeah, they have not turned left or right. They just followed the rules of physics. So very strange. Yeah.
Yeah, but this is all. I think we all here we know that comets are subject to non-gravs. So for the public, that's what we call non-gravitational forces. Think of comets as they're very rich in volatile ices, so they can have jets. And think of it as if you inflate a balloon, it will move all over the place. So with comets, it's not that dramatic, but comets do not always necessarily adhere to pure Keplerian orbit. So comets do have non-gravitational forces, and Atlas had non-gravitational forces, and the press latched onto that. The press, the media loved that. Like, oh, it's moving in a weird direction. Listen, we see non-gravitational forces in so many comets. It's so common. It's like not even like worth discussing how common it is.
Right, and that's caused by the jetting action of the gases that are coming off of a comet as they get close to the sun. So it's a natural thing. Halley's Comet returns 4 days later because of this, because of the non-gravitational forces. And our recent calculations, I haven't looked at the orbit of 3I Atlas in the last month, but up until last month, there was no need to use non-gravitational forces to do a regular solution. It's basically, there's probably some there, but it's kind of lost in the noise, so to speak. So it's not really a big deal. Before we sign off, I just want to ask Kacheng to pitch in and say, what are your thoughts on all of this?
Yeah, so I mean, this is an interesting comet as we've seen. One thing that hasn't really been pointed out yet about this comet, 3I in particular, compared to the 1I and 2I, is that it also happens to be the fastest of the three by far. And something like entering the solar system at 58 kilometers per second, I think you said. And that in itself can also create some unique just effects just from the fact that it passes through by the sun so quickly, it doesn't get a chance to be heated as much. We talked about how we should be comparing comets at similar distances from the sun due to different volatiles being released at different distances from the sun. But there's also the challenge of the fact that this comet at, say, 2 AU from the sun has experienced a different amount of heating from regular solar system comets at 2 AU from the sun, for example. And so there are even some of these things that might initially look weird about this comet might not even necessarily be inherently due to the fact that it started off weird. Or different, I should say, compared to solar system comets. It might just be from the fact that it has experienced different thermal history. And that's something else that we'll have to sort of keep in mind as we get more and more of these comets, these interstellar comets passing through the solar system at different speeds, perhaps experiencing different amounts of heating, passing different distances from the sun. And it will make for some interesting science, but very also brings a lot of challenges in making a lot of these comparisons that we would really like to make between our own comets and the comets coming in from elsewhere in the universe.
Any other thoughts before we close?
Yep, more observations needed, as always. We've got to keep on
Right.
targeting these objects, keep targeting similar distant comets, and just build up more information. I think we've got a lot of exciting times ahead of us with 4i, 5i, 6i, 7i. Let's see how far we
Exactly.
can go.
I think that our appetites are just getting whetted by this. And having so much more data on 3i than we had on 1i or 2i even just whets the appetite more. So yeah, what are the next interstellar objects going to look like? I presume that most of them will be comets, but maybe not all of them. So yeah, we'll have to wait and see.
Yeah, it could also be sort of challenging now that we're starting to get so many more of these interstellar comets show up, presumably in the next few years, since with just 3 in like the past decade or so, that's a reasonable enough spacing to where we can actually characterize each of them in detail. But say we start to get multiple per year, and then it sort of gets challenging, and it could be that perhaps none of the future comets are actually characterized in as much detail as this one, just because we have limited resources. We can't can't commandeer every single telescope on the planet to just stare at these things as they come by.
And cometary scientists tend to get low priority when it comes to big telescopes, which amazes me, Martin, when you talk about getting so much observational time on the James Webb Telescope. It's not always easy to do. Astronomers have had to struggle for decades to get observations with Hubble. So they tend to be low priority, but interstellar comets kind of, I think, raise the interest level among all astronomers, right? Not just solar system astronomers. And so it kind of brings together distant astronomy with our local astronomy, our local neighborhood.
Yes. Especially because comets are also the link maybe to life on Earth. And for other exoplanetary systems, we want to see if the same kind of processes happen, if they have also organic material and so on. And it is arriving all at the same time, where we are also understanding much better the protoplanetary disks, discovering many more, measuring their composition. And so basically all this is going to the big picture, because we found the exoplanets, we found the disk forming them. We are now having the comets coming from there. We are able to measure the abundances and composition of those disks around different kind of stars also. And so this is extremely interesting. And still for us also doing comets, and as I say, me since 25 years, all the optical spectra of comets are still looking quite alike, even if there are always some small differences. But here with the interstellar object, we see that we have 3 different objects, and with clear differences with solar system comets also. So this is extremely interesting because it will help us to understand the environment from where they come and what's going on also in the interstellar medium in the galaxy while traveling towards us.
Yeah, look forward to the party, but I won't be completely surprised if no further interstellar comets show up for the next 10 years or something like that. I think that's the amazing thing about astronomy or any science is that sometimes it will be entirely unexpected. But maybe just tons of interstellar comets show up.
I say this after Oumuamua. I say it again after Borisov. I'm not going to say it again after 3i, especially because because now
that's not good.
because now there are so many things in our heads, right, to do with these objects. Next time one will come also, and so on. But I'm afraid many of them, most of them, will be faint, or too far away from the sun, and so on.
Right. So among the last, our really good period of orbit calculation is just the last century or so, and we don't have any interstellar objects in the last century. So, and that's among hundreds of thousands of objects that have been discovered. But minor planets, comets, whatever. So I think it's. I think we probably got a little bit spoiled with 3i Atlas, but we can always hope, right?
Probably, maybe.
Yeah, they keep getting brighter. Oumuamua, Borisov, 3i.
Yes,
that's right. There's a pattern there, right? I don't think it's statistically significant, but we can always hope.
Let's see with the next one. Let's see with the next one.
Yeah. Okay. Thank you, everybody, for joining. It's been a pleasure having you here, and we'll try to get this up soon onto YouTube.
Thank you.
Okay. Thanks. How do I stop recording, Casper?
Have a good night.
Thank you.